So, how do you formally change your mind? I mean, really, think about it. It's a question we all face constantly. Today, we're going to dive into a really powerful framework for updating our beliefs when we get new information. It's a way to turn all that uncertainty out there into actual understanding.
Right, let's just start with this question head-on. How should you change your mind when you see new evidence? We do this every day, right? From tiny little decisions to huge scientific discoveries. You see a news story, you try a new workout, you get new data, and you adjust your thinking. But what if there was a principled, mathematical way to do it? Well, it turns out statistics has a pretty awesome answer.
And that answer is something called probabilistic modeling. Now, you've probably heard of machine learning models that are amazing at finding patterns. Drawing a neat line between what's spam and what's not spam. But a lot of those models, they don't really care about how the data was created. Probabilistic modeling is totally different. It's all about embracing uncertainty and trying to figure out the underlying process, the story that generated the data in the first place.
And that really gets to the heart of it. Our goal isn't just to find an answer, like yes or no, it's to find the actual probability distribution. You can think of it as the set of rules or chances that most likely cooked up the data we're looking at. It's a way deeper level of understanding. Okay, so to really get how this works, we're going to break it down into 3 key ingredients. And don't worry, we're going to use a super simple example to walk through each one, and it's all going to click into place. So, let's imagine we just found a coin on the street. And the big question is this coin fair? The true fairness of the coin, that is, the actual probability it will land on heads, is the mystery we're trying to solve. In statistics, we call this our parameter, and we'll just give it a fancy Greek name, theta. Our whole goal here is to get a good estimate for theta.
All right, ingredient number 1 is the prior. A prior belief is exactly what it sounds like. It's what you believe before you see a single piece of data. It's your initial guess, your gut feeling, your starting assumption about how the world works. It's the belief you're bringing to the table from the get-go.
So for our coin, what's a reasonable prior? Well, think about it. Most coins you run into are fair, right? It's not every day you find a trick coin from a magic shop. So our prior belief is that theta, our fairness parameter, is probably really close to 0.5, a 50-50 shot. We're not saying it's definitely 0.5, but that's our strongest initial hunch. Okay, next up is ingredient number 2, the likelihood. This is where the data finally makes an appearance. The likelihood is what connects our beliefs to the actual evidence. It asks this one crucial question. If I assume a certain belief is true, for example, if I assume the coin is perfectly fair, how likely was the data I just saw?
Let's make that real. We flip our coin one time, and boom, it comes up heads. Now we can use the likelihood to test our beliefs. So if the coin were perfectly fair, if theta was 0.5, the likelihood of seeing that heads is 50%. Makes sense. But what if the coin was actually super biased towards heads, say theta was 0.9? Well, then the likelihood of seeing a heads is 90%. The likelihood just tells us how well our different theories explain the evidence.
And that brings us to the final ingredient, the posterior. This is the big payoff. The posterior is our new updated belief. It's what you get when you mathematically combine your starting belief, the prior, with the power of your evidence, the likelihood. It's a beautiful mix of what you thought before and what the data is telling you now. So, back to our coin. After that one flip came up heads, our posterior belief has shifted. We started out thinking the coin was probably fair. The data gave us a little nudge. Now our new, more informed guess is that, well, maybe, just maybe, this coin is a tiny bit more likely to be biased towards heads than we first thought. We have officially, formally changed our mind.
So now that we have this whole prior likelihood posterior framework, how do we actually use it to get a single best guess for the coin's fairness? Well, it turns out there are a couple of main approaches. One that only listens to the data, and another that combines the data with our prior belief.
But before we go there, you have to know that this whole idea was, and this is not an exaggeration, incredibly controversial. The very concept of a prior belief, of starting with some kind of assumption, seemed totally unscientific to a lot of people. In fact, one of the absolute giants of statistics, a guy named R.A. Fisher, hated it. He thought it was a fundamental error and that the whole thing should be thrown out.
So why on earth did this idea not just survive that criticism, but actually thrive? Well, it's because that controversial ingredient, the prior, is secretly a superpower, especially when you don't have a whole lot of data. Let's look at exactly why your starting point matters so much.
Okay,
This is where it all clicks. Look at the difference here. On the left, you have the data-only approach. It's called maximum likelihood, and it leads to a conclusion that's, frankly, absurd. You flip a coin once, it's heads. This method concludes the probability of heads is 100%, forever, no more tails for you. But look at the right. The Bayesian approach takes our prior belief that the coin is probably fair and combines it with that same single flip. And it gives us a much more sane answer. Yeah, the coin might be a little biased towards heads, but 100%? No way. That's way too extreme.
Here's a really cool way to think about it. A prior basically acts like you're starting with some imaginary or hallucinated data. That belief that the coin is probably fair, it's kind of like starting your experiment with a couple of imaginary heads and a couple of imaginary tails. Already on the scoreboard, it provides a buffer, a little bit of common sense, that stops the model from freaking out and jumping to crazy conclusions based on a tiny bit of evidence. And that right there shows why this whole concept is so incredibly powerful. This isn't just some philosophical game we play with coins. This way of thinking has huge applications in the real world, solving really complex problems that we see every single day.
Think about trying to predict something rare, like credit card fraud. If you go a full day with zero fraud, a data-only model might conclude that fraud is impossible. A Bayesian model, with a prior, knows better. It's used in spam filters to weigh the weird words in a new email against all the prior knowledge of what spam usually looks like. It's the engine behind models that can discover hidden topics in millions of documents. And it helps build more stable prediction models by preventing them from overreacting to every little bit of noise in the data.
So at the end of the day, what we've really been talking about isn't just some nerdy statistical tool for data scientists. It's a mental model. It's a fundamental framework for how to think, how to learn, and how to reason when you don't have all the answers. It teaches us how to carefully, thoughtfully weigh new evidence against what we already know to get a clearer, more accurate picture of the world.
And that leaves us with one last question for you. This whole framework, it gives us a powerful, structured way to change our minds. It's about being a little less certain, a little more curious, and always being ready to update. So if you look at your own life and the world around you, what beliefs should you be updating today?